All right, so here we are in question 1. On the axis, sketch the graphs of y equals 2x plus 5 and y equals mod 4x minus 3, stating the intercepts with the coordinate axes. Okay, well, I think let's just sketch each graph one by one. So if we've got y is equal to 2x plus 5, we want to find the x-intercept and the y-intercept of that. The x-intercept is when y is equal to 0, right? The reason for that is on the x-axis, the y-coordinate is always equal to 0. And if we set that equal to 0, then we're going to get x is equal to negative 5 upon 2, okay? And the y-intercept is when x is equal to 0. And the reason for that is everywhere on the y-axis, the x-coordinate is 0. And so we're going to get y is equal to 5, okay? So that's the x-intercept and the y-intercept for that function. Now, for the second one, y equals mod 4x minus 3. I think the easiest thing to do first is to sketch the graph without the modulus. So we're going to sketch y equals 4x minus 3. So y is equal to 4x minus 3. And the x-intercept for that will be when y is equal to 0 again, which means that x is going to equal to 3 upon 4. And similarly, the y-intercept is when x is equal to 0, so y would be equal to negative 3. So I think let's try to sketch these on. So I'm going to indicate points on here. So I know 1, 2, 3, 4, 5, 6, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. Y, we're going to want to go a little bit more, so I don't know, maybe that'll be 2, 4, 6, 8. Okay, minus 2, minus 4, minus 6, right? So 1, 2, 3, 4, and so on. 2, 4, 6, just to indicate the scale there. Okay, so the first graph we said the x-intercept is at negative 5.2, which is negative 2.5, so that is there. And the y-intercept is at 5, so that's there. So we can draw a straight line that goes between those. So I'm going to try to draw that like that. That's about that, right? So that is the graph y equals 2x plus 5. I'm just going to make sure I label that y-intercept as 5 and that x-intercept as minus 5.2. And then the second graph, well, I'm going to sketch 4x minus 3. So the x-intercept of that was 3/4. So that's like there. And the y-intercept was negative 3. So that's there. And so that graph, if I was to draw it out, let's try to draw a straight line, would look something like that. Okay, so actually I'll just extend that blue line as well. And that blue line, whoop. So, something like that. Okay, and now the thing is, what happens with the modulus, right? What does the modulus do to this function? Well, the job of the modulus is to take a positive number and to keep it the same, right? So the modulus of positive 5 is just 5. But what it does is it takes a negative number and turns it into a positive, right? So the modulus of negative 3 is positive 3. So when the graph has got negative values, in other words, when we're below the x-axis, then the modulus is going to take all those negative values and turn them into positive values. And what that's going to look like is a reflection in the x-axis. For example, this point here, where y is equal to negative 3, is going to get reflected to the coordinate y is positive 3. So what we can do is we can just draw that on like this, like that. Because each one of these y coordinates, when you put it into the modulus, becomes reflected like that. So I'm just going to get rid of the rest of the graph. Like that, like that, like that. Okay, I'm just going to label on the points so that I make sure I get the marks. That there is 3/4. And the y-intercept was at 3 there. And yet for the blue line, we've got x-intercept negative 5.2, y-intercept of 5. And I'll just label that. Y is equal to mod 4x minus 3. Okay, then part B of this question, we want to solve the inequality mod 4x minus 3 is less than 2x plus 5. Well, we can do that now by looking at our graph, right? Because we want to find out where the green graph, which is mod 4x minus 3, is less than the blue graph, 2x plus 5. So where is the green graph less than the blue graph? Well, it's everything from here all the way up to here, right? So in other words, these key points here and here tell us where the green graph is going to be less than the blue graph. So all we want to do is want to find those. And those are going to be points of intersection. Well, how are we going to find those points of intersection? Well, let's look at this guy. This guy is going to be the intersection of the line 2x plus 5, that blue line, with the line 4x plus 3. Now why is that? Well, because remember the line 4x minus 3 was that whole thing. Right? We sketched that first in part A. And when we're above the x-axis, the modulus doesn't actually change the function. Okay, so 4x minus 3, if the value is positive, it remains the same as 4x minus 3. So this guy is going to be the intersection of 2x plus 5 and 4x minus 3. So let's try to solve that. So we're going to find the intersection there of 4x minus 3 is equal to 2x plus 5. So if we rearrange that, we get 2x is equal to 8, and that is x is equal to 4. And just if we go up and look at our graph, that should basically be right, isn't it? Because hopefully we've drawn our graph relatively accurately. Yeah, and that to me looks right, that x is equal to 4. Okay then, how do we get the second point here? Well, this is the intersection of the line 2x plus 5, right, the blue line. But what's this guy here? This guy is the reflection of 4x minus 3 in the x-axis, right? So remember that the line 4x minus 3 did that. That's the whole thing. But this part of that line, the part where it's negative, became reflected in the x-axis, so it became that. So this part of the line isn't 4x minus 3. What it is it's 4x minus 3 reflected. Now, the way you can think about that is to say we took 4x minus 3 and we multiplied it by negative 1. Right? So what we've got here is we have got 4x minus 3, but multiplied by negative 1 is equal to 2x plus 5. Now, if you're unsure about that, let me just try to explain it to you. Earlier I said that the function of the modulus is to turn a negative number into a positive, right? So the mod of negative 3 is equal to positive 3. Well, how else could we think about that? We could say that what the function mod negative 3 does is it multiplies negative 3 by negative 1, okay? Because if you multiply negative 3 by negative 1, you get positive 3. So the function of the modulus is kind of like this. If the number on the inside is negative, then the modulus multiplies by negative 1. But if the number on the inside is positive, then there is no change. Or you could think of it, we multiply by positive 1, right? Which means there's no change. So in the first part, 4x minus 3 was positive, so there was no change. We just treat that as 4x minus 3. But for the second intersection, 4x minus 3 was negative. So what we do is we multiply it by negative 1 to turn it into a positive. Okay? So then what we've got to do is just got to solve that. Negative 4x plus 3 is equal to 2x plus 5, which means that 6x is equal to negative 2, which means that x is equal to minus a third. And again, that should tally up with our graph. So if I was to go back to my graph, I was to say, what's that x coordinate there? Yeah, I could believe that x coordinate is negative a third. So what are the values that we're interested in? We are interested in values that go from negative a third all the way up to 4. Okay, so the end answer is x is between negative a third and 4. And remember, we're using less than signs and not less than or equal to signs. And the reason for that is the inequality we're asked to solve is a less than, not a less than or equal to. Okay, so that is important. All right, so here we are in question 2. The perpendicular bisector of the line joining these 2 points passes through the point 2k. We want to find the value of k. Well, it's probably a good idea if we recap the idea of a perpendicular bisector. So let's say we've got 2 points here, A and B, and we've got a line that connects them like that. So just draw that line. What is the perpendicular bisector? Well, it is the line that runs perpendicular to AB and that cuts it into two, right? Bisector literally means to cut into two. So we need to find the midpoint of this line, right? Because the midpoint is the point that divides it into two equal parts. And so the perpendicular bisector is going to look like that, right? Where that is a right angle. Okay, so if we want to find the perpendicular bisector, we need to find the gradient perpendicular to AB, and we need to find the midpoint of AB. So let's do that. Let's find the midpoint first. That's found by adding up the two x coordinates and dividing by 2, and adding up the two y coordinates and dividing by 2. Okay, so if we do that, negative 3 plus 6 is positive 3, divided by 2 is 3 upon 2. And 2/3 minus 7/3 is minus 5/3. And minus 5/3 divided by 2 is minus 5 upon 6. Okay, so that's the midpoint. Then what we want to do is want to find the gradient. And if we do that, we're going to get y2 minus y1, so the change in the y values. So we got negative 7/3 minus 2/3, all divided through by the change in x, which is 6 minus minus 3. So here we got 6 minus minus 3. We want to be extra careful about that. And negative 7/3 minus 2/3 is minus 9/3. And minus 9 divided by 3 is minus 3. And then 6 minus minus 3 is 6 plus 3, which is 9. So the gradient here is negative 1/3. Now what we want is not the gradient of AB, but we want the gradient perpendicular. And hopefully what you know is that if two gradients are perpendicular, m1 and m2, then their product is equal to negative 1. So we can find the gradient perpendicular, so I'll write it like that, the gradient perpendicular, by doing negative 1 divided by minus 1/3, and negative 1 divided by minus 1/3 is 3. Okay, so now just to clarify, we want the line which has got a gradient of 3, and it goes through the midpoint, which is this point here, 3 upon 2, negative 5 upon 6. Okay, so we can now do that by using this formula. Y minus y1 is equal to mx minus x1. Okay, so our y coordinate point was, let's go up again, negative 5 upon 6. Our gradient is 3. And our x coordinate was 3 upon 2. Okay, and I think probably a good idea just to rearrange this. So this is y plus 5 upon 6 is equal to 3x minus 9 upon 2. And so y is equal to 3x minus 9 upon 2. I'm going to change that into 6, so minus 27 upon 6. Minus 5 upon 6, like that. And that's equal, therefore, to 3x minus 32 upon 6. Okay, so that's the equation of the perpendicular bisector. Now, we are told that this line passes through the point 2k. We want to find the value of k, so we just substitute in x is equal to 2. So this goes through the point 2k. So when x is equal to 2, y is equal to k. So k is equal to 3 times by 2, which is 6, minus 32 upon 6. Well, 6 can be rewritten as 36 upon 6. And so 36 upon 6 minus 32 upon 6 is 4 upon 6, and 4 upon 6 is 2/3. So k should be equal to 2/3. Okay, here we are in question 3, which is a trigonometric graph sketching question. On the axis below, draw the graph of y equals 2 sine a third x minus 1 for x is between negative 360 and positive 360. Okay, now in order to do this question, I always recap the basic principle, which is if I've got a graph of the form y equals a sine bx plus c, we want to think about what each of those terms mean. Let's go in reverse order. C is the shift in the y direction. So that tells us the position of the center line. What I mean by center line is when you've got a sine or a cosine, right, the center line is the x-axis, right? The wave oscillates above and below the x-axis. So if c is like +1, then what happens is the whole graph gets shifted up by 1. So the center line becomes y equals 1. All right. Okay, next one. Let's do B. B is often the most tricky. So B here is the number of waves in 360 degrees, or 2 pi if you're using radians. Now, students find this one the hardest. If I ask most people, what does this represent? They say it's the period. Now, that's not right. It tells us about the period, but the number here isn't actually the period. It's a different thing. So let me try to clarify. The period is how big is one wave, right? So how big one wave. But the number b there is the number of waves in 360 degrees. So it's like the frequency for every 360. So let's try to think about that. Let's say the number b was 2. What that would mean is that there are 2 waves in 360 degrees. Now, if that's the case, how big would one wave be? Well, if there are 2 waves in 360, then one wave is going to be 180, right? Because it's 360 divided by 2. If we were to say, let this number be a 3, what does that mean? It means that there are 3 waves in 360. And if there are 3 waves in 360, how big is each wave? Well, it would be 360 divided by 3, which is 120. So if you want to get the period, right, so the period is what we denote by t, big T, then that's equal to 360 degrees divided by b. Okay, or 2 pi divided by b if you're using radians. Now, the thing is, right, this should make sense. If you know the definition, it should make sense. So as I try to encourage all my students, don't guess. Try to have precise definitions for all of these things, and then be able to reason out what the period is, right? So if you know that this guy represents the number of waves in 360, then you know that each wave, the time period, will be 360 divided by that number. Okay, hopefully that should make sense. And A is the amplitude, okay, the last one, which is the stretch in the y-axis. So if we've got the graph, let's say sine x, that bit goes between +1 and -1. So 2 sine x is going to be stretched. It's going to go up to +2 and -2. 3 sine x will go up to +3 and -3, like that. All right, now, let's go up to our graph here. We have got the graph of 2 sine a third x minus 1. So if I'm going to list that out, what I'm saying here is that my A is equal to 2, that's my amplitude, my B is equal to a third, and my C is equal to -1, okay? So what's this going to mean? We're going to have a graph that's shifted down by 1, so the center line is going to be -1. So why don't I just draw that on right now? So the center line is going to be -1. That is that guy there. Okay. That's going to be my center line. Okay, what else do we know? Well, we're told that our value of b is a third. Well, what we need to do is we need to find out what the period is from that. So the period will be 360 divided by a third, which is the same thing as 360 times by 3, right? So 300 times by 3 is 900. 60 times by 3 is 180. So that's going to be 1080 degrees. So we're looking for a wave where one full wave is 1080 degrees. How's that going to look like on this graph? Well, it's going to be jolly difficult, isn't it? Because we don't have 1080 degrees here. So we can't actually draw a full wave that starts here and goes on. So what can we do? Well, how big is half a wave? Half a wave is going to be 540, isn't it? And how big will be a quarter of a wave? A quarter of a wave will be 270. Right, so why don't we start with that? We know that a quarter of a wave will be 270. And if we know that basically a sine wave, sorry to just draw on here, one sine wave looks like that, right? Then the first quarter of the wave is the bit that goes from here all the way up to there, right? So from here to here, okay? So what we know is that a quarter of a wave is going to take us to 270. So our wave is going to start here, and the first quarter is going to be at this point here, 270. Right. Then lastly, what does A tell us? A is 2, isn't it? So A is 2, the amplitude is 2. What's that going to mean? It means that we're going to go up from the center line by 2. Well, if we go up from the center line by 2, we go 1, 2, we go up to positive 1. And we're also going to go down from the center line by 2, 1, 2, down to negative 3. So what we could also draw is we could say, well, like these are going to be our maximum points for the graph, like that. And this is going to be the minimum point for the graph, like that. And so now just joining up what we said earlier, if the first quarter of the wave is at 270, then that's going to go up to there, right? Because the first quarter is where we get our peak. And we can also do it on the other side. We go to negative 270, we're going to have our trough there. So that should be enough information to be able to draw out this graph. So if I draw it out, I think I'm going to get something like, I'm really sorry, I'm not good at drawing these. Like that. Like that. Like that. Okay, shouldn't be so wobbly in the middle. I'm drawing it on a tablet, guys. It's a little bit harder. Okay, but the wave should look something like that. Okay. Now, you should really aim to understand all of those things. But if you can't do that, then what could you do as an alternative? Well, you could just plot points, couldn't you? Right? You've got 90, 180, 270. So what you could do is you could put x is 90 degrees into the formula, get a point. X is 180, get a point. X is 270, get a point. X is 360, get a point. Yeah, you could do that if you're really stuck. But all of these questions are essentially the same format. They require you to understand A, B, and C. And I think if you just put a little bit of effort there into knowing those definitions, then sketching these graphs actually isn't too bad with a little bit of practice. Okay, then this is question 4, which is a factor theorem, remainder theorem style of question. Before we do this, I think it's helpful to review what the factor theorem and remainder theorem are. So let's have a quick look. We'll start with the remainder theorem. The remainder theorem states that if I get a remainder r when I divide a polynomial by x minus a, then if I substitute a into the polynomial, I will get remainder r. Okay, so let's just think about that a little bit more carefully. Imagine I've got a polynomial here, and I do polynomial division where I divide it by x minus a. In the end, I get a remainder r. Well, if that's the case, then we know that if I was to take a and to substitute it into the polynomial, I will get the same value as the remainder. I will get r. Okay, now let's think about the factor theorem. The factor theorem is actually a statement of the remainder theorem for a specific case. We'll think about that a bit more in a moment. But the factor theorem states that if x minus a is a factor of the polynomial p of x, then that means that x equals a is a root. Now, let's just think really, really carefully about that. If x minus a is a factor, that means that if we were to divide p of x by x minus a, we're going to get a remainder of 0. So in other words, this statement here is basically the same thing as saying that the remainder must be equal to 0. Okay, that's basically what that means. And so if we were to use the remainder theorem, then that would mean if we substituted a into our polynomial, we should get a remainder of 0, right? So if we did p of a now, then what we would get is we would get 0. But hang on, when p of a equals 0, that's the same thing as saying that a is a root, right? That is a definition of a root there, because a root is an x-intercept. It's a place where the y-coordinate is 0. It's a place where the polynomial is equal to 0. So this thing is just another way of saying that a is a root. So if x minus a is a factor, a is a root, because that's just another implication of this thing here, the remainder theorem. So in a way, what I'm trying to stress here is not only knowing the definition of remainder theorem and factor theorem, but also that these two are not separate things, right? They're not like two different theorems. Actually, the big theorem is the remainder theorem, and the factor theorem is like a specific instance of that. It's the instance where the remainder is 0. Okay, so actually I find that the textbook to be really quite irritating in this way, because what it does is it teaches you the factor theorem first, and then it teaches you the remainder theorem second. As if the remainder theorem follows on from the factor, but actually it's the other way round, isn't it? Right? The big idea is remainder theorem, and the factor theorem is like the kind of the specific case of that. All right, now let's go down and let's look at the question. The polynomial x is given by this thing here, where a and b are integers. P of x has a factor of 2x plus 1, and it has a remainder of -6 when divided by x plus 1. We want to find the values of a and b. Okay, well, if it's got a factor of 2x plus 1, then we can set that factor equal to 0 to find out what the root is. And so that root is going to be equal to -1/2. Now, if the root is -1/2, that means that if we substitute -1/2 into the polynomial, I should get 0. Okay, so let's just try that. I'm going to get a times by -1/2 cubed. Well, -1/2 cubed is -1/8, so that's -1/8 a, plus b times by -1/2 squared, which will be +1/4 b, plus 3 times by -1/2, which is -3/2, plus 2 is equal to 0. Now, that's all going to be quite irritating to deal with, what with all those fractions. So what we're going to do is we're going to take the entire polynomial and we're going to multiply it through by 8 to get rid of all of those fractions. So -1/8 times by 8 is going to be -1, so we get -a. 1/4 times by 8 is going to give us 2, so that's 2b. -3/2, if I times that by 8, then it's 3 times by 4, so that's going to be -12. And then 2 times by 8 is 16. So we get that is equal to 0. And we'll just simplify that a little bit. We'll get -a plus 2b is equal to -4, right? Because -12 plus 16 is +4, but I bring it to the other side. Right, I'm going to label this guy here equation 1, all right? Because we're going to get another equation in a moment. Okay, second statement. We are told that P of x has a remainder of -6 when it's divided by x plus 1. Well, if we use the remainder theorem, that tells us that if we were to substitute in -1 into the polynomial, we should get -6. Why is it -1? Well, if we just go back to the remainder theorem just for a second, right? It says that if we divide by x minus a, then if we substitute a in, we get r, right? So it's x minus a here. So how can we think about x plus 1? Well, we could think about x plus 1 as being x minus -1, right? So hence that's why we substitute in. So I'm going to do p of -1 is equal to -6. So if I do all of that, I'm going to get a times by -1 cubed, which is going to be -a cubed, right? Because negative times negative times negative is a negative. Sorry, not -a cubed, just -a, beg your pardon. Plus b times by -1 squared, so that's going to be +b. What else was it? Plus 3 times by -1, so that's -3. And then plus 2 is going to equal to -6. So I think if I simplify that, I get -a plus b is equal to, well, -3 plus 2 is -1. I add 1 to both sides, I get -5. And so that's going to be my equation 2, right? So I've got two equations in terms of a and b. What's the best way to deal with those? Well, I think elimination, isn't it? I'm going to do equation 1 minus equation 2. And so that means I'm going to get -a minus a, that's 0. 2b minus b, that's b. And then -4 minus -5, that's +5. So b is going to be equal to 1. And if b is equal to 1, well, I can substitute that into here. I'm going to get -a plus 1 is equal to -5. Therefore, -a is equal to -6. And that means that a is equal to +6. Okay, I'm just going to check my answers for that against the mark scheme, make sure that I am correct. So yeah, a is 6 and b is 1 are the right answers. Okay, then part B of this question, we want to show that p of x equals 0 has only one real root. Well, we'll substitute in our value of a and b, which were 6 and 1, into the polynomial. And we also remember from part A of the question that 2x plus 1 was a factor. Well, if 2x plus 1 was a factor, then we should be able to divide this entire polynomial by 2x plus 1. So why don't we do that? Let's do some polynomial division. So I'm going to divide this whole thing by 2x plus 1. Okay, so how do we do polynomial division? Well, this guy here is what we call the leading term, 6x cubed. So we're going to divide that by 2x. 6x cubed divided by 2x is 3x squared. I then take that 3x squared and I multiply it with the divisor here. If I do that, I get 6x cubed plus 3x squared. And having done that, I'm then going to subtract this off from our polynomial. So we're going to do 6x cubed minus 6x cubed, which is 0. X squared minus 3x squared is minus 2x squared. So I get minus 2x squared there, plus 3x plus 2. Okay, well, that means that minus 2x squared is our new leading term. That's going to be divided by 2x. And if I do that, I'm going to get negative x. Okay, and I take that negative x and I multiply it through by the divisor. If I do that, I get minus 2x squared minus x like that. And again, what I'm going to do is I'm going to subtract off. By the way, just as a quick tip, I strongly recommend that you put your negative sign on the right-hand side, right? Very often I see students put the negative sign like here and here. And I think the danger of that is you can confuse what's going on. You end up thinking this is negative 6x cubed or something like that. So just keep it out the way so you don't get mistaken. Okay, minus 2x squared minus minus 2x squared is plus 2x squared, so that's 0. 3x minus minus 3x is 4x, so we get 4x plus 2. And of course, that means that 4x is our new leading term. We divide it by 2x, and we get 2. And we multiply 2 by 2x plus 1, we get 4x plus 2, which is what we want, because if we subtract that off, we get 0. If at the end you don't get 0 here, it either means that you've done your polynomial division wrong, or it meant that your answer for part A was wrong, because these values A and B are not going to be correct. Okay, now what does this mean? We've taken our polynomial, haven't we? Call it P of x. We've divided it through by 2x plus 1, like that. And what did we get at the end of that? We got 3x squared minus x plus 2, right? So 3x squared minus x plus 2. So this thing here is just restating the operation we've done. We divided the polynomial by 2x plus 1, and we ended up with that. Well, if we multiply both sides by 2x plus 1, then we're going to end up with this guy here. 2x plus 1 times by 3x squared minus x plus 2. By the way, this statement vindicates the factor theorem, isn't it? Because if we just think about it, if I was to substitute in negative a half into here, right, which is a root, then this term here, this corresponding factor is going to be equal to 0, and 0 times by anything is 0, right? So we kind of show the connection between the root and the factor here. Now, what was the question? The question was to show that we only have one real root. Well, if that's going to be the case, then this guy here, this quadratic factor, can't factorize anymore, won't be able to give us any real roots. When will a quadratic not have any real roots? When the discriminant, b squared minus 4ac, is is negative, right? It's got to be less than 0, okay? So if that's the case, if b squared minus 4ac is less than 0, then there are no real roots. So that's what we're going to do. We're going to calculate b squared minus 4ac for this polynomial. So our b is negative 1, so we've got negative 1 all squared, minus 4 times by a, which is 3, times by c, which is 2. Well, negative 1 squared is 1, and 4 times by 3 is 12, times by 2, 24, so we've got minus 24, and that's negative 23, and the whole point is that is a negative, right? So this guy, that guy is negative discriminant, therefore, there are no other real roots. Okay, so the only real root, is the one we already knew, which is x is equal to negative a half. Okay, and that's the answer to that part of the question. All right, then here we are in question 5, which is a permutations combination style question. At the start of all these questions, I like to recap the difference between permutations and combinations. So here we are. What is NPR? NPR is the number of ways to arrange R items taken from N items. And what is NCR? It is the number of ways to choose R items taken from N items. Now, what does that mean? In arrangements, order matters, okay? Whereas for combinations, order doesn't matter. So let's think about the classic distinction. I want to make a password. In a password, it's not just that I have the right letters, I need to have the right letters in the right order. So order is important, so I would use combinations. Whereas if I'm selecting a team and I want to choose 5 people, then it doesn't matter the order in which I choose those 5, so long as I've got those 5 people. And generally what happens is in the question, context determines whether or not order matters or doesn't matter. So what you don't want to do is you don't want to say to yourself, this question's got letters, therefore it's permutations, or this question has got people, therefore it's combinations. What you want to do is you instead want to reason out, in this particular circumstance, is the order going to be important? Now, let's read the question. We've got a 5-character password. If it's a password, then the order is going to matter, isn't it? Right? Because if I had the letters A, B, C as my password, that is not the same thing as C, A, B, right? Those two things are different because the order is important. So we're going to be using permutations here. Now, we've got 10 characters. Want to form a 5-character password. Find the number of passwords that can be formed if there are no restrictions. Well, if we've got 10 characters to choose from, and I'm arranging 5 out of those 10, that is going to be 10p5. Okay, so 10p5. So let me just put that into my calculator. 10p5. I get 30,240. Okay. All right, then, part B, find the number of passwords that can be formed if the password has to contain at least 1 symbol. So we can imagine if it's got 1 symbol, 2 symbols, 3 symbols, or 4 symbols. But the easiest way to think about this is to imagine the situation that you can't have, which is if we've got no symbols. Okay, so we're going to think about that. What if there are no symbols? Well, that means that we would have to choose our 5-character password out of the 6 letters only. So we are arranging 5 items taken from 6 items. So that would be 6p5. So 6p5, if I just do that, 6p5 is equal to 720. Okay. And if we know that the total number of passwords that we can have is 30,240, and the number of ways in which there are no symbols is 720, then the number of ways in which there is at least 1 symbol has got to be 30,240 minus the 720, right? Because this represents all the ways, and this represents all the ways where there is no symbol. So every single other way has got to have at least 1 symbol in it. So let me just calculate that. 30240 minus the answer is 29,520. So 29520. Okay. All right, part 3, find the number of passwords that can be formed if the password has to start with 2 letters and end with 2 symbols. So 1, 2, 3, 4, 5. I think it's easiest to draw it out. We're going to have 2 letters at the start and 2 symbols at the end. Okay, well, let's start with the letters. So I want to arrange 2 letters taken from 6 letters. Okay, so how can I arrange 2 letters taken from 6? That is going to be 6p2. That's the letters at the front. And then how can I do the symbols at the end? Well, I want to arrange 2 symbols taken from 4 symbols. So how many ways can I arrange 2 symbols taken from 4? That would be 4p2. And then lastly, we've got a thing in the middle. Well, that can be either a letter or a symbol. It doesn't matter. So we started with 10 different items here. We've used 2. So we have 8 remaining to choose from. And so, oh, sorry, not chosen 2. We've chosen 4, beg your pardon, right? Chosen 4 out of these. And so we've got 6 remaining. So there are 6 different ways I can fill up that middle slot there. Okay, so now what we've got to do, we've got to multiply these guys. Why are we multiplying them? Well, essentially, the short way to answer that is if we've got and, then we multiply. If we've got or, then we add. That's kind of a helpful rule of thumb. And in this situation, we want to have the two letters at the beginning and the two letters at the end and the character in the middle. So that's why we're going to multiply. Okay, so I'm just going to calculate this. I'm going to do 6p2 is 30 times by 6 times by 4p2. So 4p2 is 12. So I need to do 30 times by 6 times by 12. And I get that as 2160. Okay, so this is part B. A team of 8 people is to be chosen from 5 doctors, 4 teachers, and 6 police officers. Find how many possible teams have the same number of doctors as teachers. Well, again, we need to think about this combinations, permutations thing. So let's just revisit that. Permutations is the number of ways to arrange our items taken from n, and combinations is the number of ways to choose. The distinction is that with permutations, order matters, whereas with combinations, order doesn't matter. So in this context, the order in which we choose our team is irrelevant. So therefore, we're going to be using combinations. That's the first and most important thing. The next thing is really just to lay out the information in a helpful way. We want to have a team of 8 people where the number of doctors and teachers is the same. So let's draw a chart. We've got doctors, teachers, and police officers like that. Well, what we could have is we could have 0 doctors, 0 teachers, but that would require that we have 8 police officers, and that's not possible, right? So that doesn't exist. Alternatively, we could have 1 doctor, 1 teacher, which means we would have 6 police officers. Or we could have 2 doctors, 2 teachers, which means we'd need 4 police officers. Or we could have 3 doctors, 3 teachers, and that means we'd have 2 police officers. Or we would have 4 doctors, 4 teachers, and then we would have 0 police officers. Okay, so I think that's probably the best way of laying out the information. And so then what we've got to do is just got to kind of fill that up. So we can ask, well, how many ways can we choose 1 doctor or 2 doctors, 3 doctors or 4 doctors? Well, we're choosing from 5 doctors in total. So the way of choosing 1 doctor would be 5C1. How many ways could I choose 1 teacher? That would be 4C1 because we're choosing from 4. And how many ways could I choose 6 police officers? That would be 6P6, right? So I'm not 6P6, 6C6, do beg your pardon, because I'm choosing 6 officers from 6 officers. Now, what am I going to do with these guys? I'm going to have to multiply them, right? And the reason I'm multiplying them is because of the difference between and or. Remember, if we've got and, we need to multiply. If we've got or, we need to add. So in this particular case, we want 1 doctor and 1 teacher and 6 policemen, okay, or 6 police officers. So therefore, we multiply. Well, we've got to do this for all of the remaining elements. So I'll just do that. So 5C2 here, 5C3 here, 5C4. And then that will be 4C2, 4C3, C3, beg your pardon, 4C4. And then this will be 6C4, 6C2, and 6C0. And of course, we're going to be multiplying all of these. Okay. And so now I need to calculate each of these guys. I'll key this into my calculator. Well, 5C1 is 5, 4C1 is 4, and 6C6 is 1. So 5 times 4 times 1, that's 20. Okay, I'm going to calculate the other two. So 5C2, that's 10. 4C2, I think that's 6, isn't it? So times by 6. And then 6C4 is 15. And then next row, 5C3 is 10. 4C3 is 4. And 6C2, it's going to be the same thing as 6C4, that's 15. 5C4 is going to be 5. 4c4 is 1, and 6c0 is also 1. So let's just simplify all of those as well. So we've got 20 there. So we want to do 10 times 6 times by 15, 900. 10 times 4 times 15, 600. And 5 times 1 times 1 is 5. Well, now what we've got to do with all of these? Well, we've got to add them up. Why are we going to add them up? Because this is or, isn't it? We've either got the situation where we've got 1 doctor, 1 teacher, and 6 policemen, or 2 doctors, 2 teachers, and 4 policemen, or 3 doctors, 3 teachers, and 2 policemen, or 4 doctors, 4 teachers, and 0 policemen, right? So these represent 4 different cases. So we need to add up all the alternatives. And if we add that up, we're going to get 20 plus 900 plus 600 plus 5 is 1525. And that should be our answer. Okay, so here we are in question 6. We've got a polynomial q, which is given by that. We want to find the x-coordinates of the stationary points of the curve. Now, what we've got here is we've got the product of two functions, right? We've got this function here, negative a third 2x minus 1, times by this function here, x plus 3 squared, right? So we've got two functions multiplied together. So we could say we've got the product of two functions, right? Because product means we multiply, like the product of 3 and 5 is 15. And so we're going to use the product rule. So let's try to do that nice and slowly. We're going to choose the first function. We're going to call it u, is negative a third 2x minus 1. I'm going to write it like that to the power of 1. And we've got v here, which is x plus 3 to the power of 2. And what we've got to do is we've got to differentiate both of these guys. We've got to find u prime and v prime. Now, I'm going to start with v. How do we differentiate a function like that? Well, we're using the chain rule here. And what we do when we use the chain rule is we take the big function, which is, in this case, the bracket squared, and we differentiate it. So I'm going to bring the 2 down to the front, and I'm going to subtract 1 from the power. So I do that, I get 2 bracket to the power of 1, right? So I differentiate the big thing. Then what I do is I look on the inside, and I differentiate that. So x plus 3, if I differentiate it, I get 1. I multiply through by 1. Now, even though that's unnecessary in this case, I think it's a really helpful habit to have, okay? Now this guy here is probably better. You could like differentiate the big bracket and so forth, but I think it's just easier to say this guy is equal to negative 2/3 x plus a third, right? Because then if you differentiate that, all you're going to get is negative 2/3, okay? Because the 1/3 differentiates to give 0, okay? I'll get rid of that. However, I sort of want to indicate that you can do it the same way. So imagine I differentiate the big bracket here. So I bring the 1 down to the front and reduce that power by 1. That would give me, so u prime would equal to negative a third, kind of times by 1, 2x minus 1 to the power of 0. Now differentiate inside that bracket. So I differentiate the 2x minus 1, I get 2, and I multiply through by the 2. Well, 2x minus 1 to the power of 0 is just 1, right? Because anything to the power of 0 is 1. So what I'm left with is negative 2/3, right? So it's important to demonstrate that the rules that we learn are consistent. That's always a helpful thing. But, you know, usually some ways are faster, easier than others. So I suggest that you try to have a variety in your methods so that you can use the most appropriate tool. Okay, then what's the product rule? Product rule is v du plus u dv, right? I write it in that order because it's the same order as the quotient rule, which is v du minus u dv, so it means you don't make a mistake with the quotient rule. Then what I'm going to do is I'm going to substitute in. So my v is x plus 3 to the power of 2. That's equal to x plus 3 to the power of 2 times by du, which is negative 2/3, plus u dv. So u is negative a third. So I'll write that like negative a third, 2x minus 1 times by dv, which is 2x plus 3, like that. Now, it's probably a good idea to factorize, isn't it? So we want to see what our common factors are. And I think we've got a common factor here of x plus 3 and x plus 3. And we've also got another common factor, which is negative a third. So what I'm going to do is I'm going to factorize that out. So I'm going to get here negative a third x plus 3. Now, if I do that from the first term, then what I'm going to be left with is 2 bracket x plus 3. And if I factorize out from the next term, I'm going to be left with 2 times by 2x plus 1. So plus 2 bracket 2x minus 1. Okay. And so then I'm going to simplify inside that bracket. So I got negative a third x plus 3. So here I've got 2x plus 4x. So 2x plus 4x is 6x. And then I've got 2 times by 3, which is 6. 2 times by negative 1, which is negative 2. So 6 minus 2 is positive 4. So we've got 6x plus 4. And of course, what we could do is we could factorize out the 2 as well. So we get negative 2/3 bracket x plus 3 times by 3x plus 2. Now, the question in this case is to find the stationary points. So the stationary points are when y prime is equal to 0. So we set this whole thing equal to 0. And that's going to give us two options, isn't it? Either x plus 3 is equal to 0, which means that x is equal to negative 3, or 3x plus 2 is equal to 0, and so x is equal to negative 2/3. Okay, so those are going to be the x coordinates of our stationary points. And we're not asked to find the y coordinates, right? The question just says the x coordinates there. But if you got to be careful with these questions. If it says coordinates, then what you'd have to do is you'd have to substitute your values into here to get the y values as well. So I'm just going to quickly check my answer, negative 3 and negative 2/3, see if that is right. See, negative 3 and negative 2/3 is the correct answer. All right, so continuing on with this question, part B is we want to sketch the graph of q of x, stating the intercepts with the coordinate axes. Now, this is a cubic graph. That's the first thing, isn't it? Because we got an x squared term in here. It's going to be times by another x. We're going to get an x cubed. Now, what do cubics look like? Well, if we've got a positive cubic, it's going to look like that. So that's positive cubic. If we've got a negative cubic, it's going to look like that. It's going to be sloping down. So we just got to ask the question, which one have we got? Well, we're going to get an x times by a positive x squared. So that's going to be a positive x cubed, but then times by a negative number. So we're going to get a negative x cubed. So we're going to have a graph that's going to look something like that. So that's the first step. Second thing is, where are the x-intercepts going to be? Well, the x-intercepts we can get by looking at this graph because it's already in factorized form. So 2x minus 1, if we set that equal to 0, we're going to get x is equal to half. That's one of the roots. And x plus 3, if we set that equal to 0, then we're going to get x is negative 3 is another one of the roots. So we can immediately write, so x-intercepts when y is equal to 0. And that's going to leave us either with 2x minus 1 is equal to 0, which is x is equal to a half. So it's always good to state you're working. And we've got x plus 3 is equal to 0, which means that x is equal to negative 3. But we need to think about that last one a little bit more, because this is x plus 3 squared. So what's that squared mean? It means actually we've got two roots at negative 3, right? This is a repeated root. And what does a repeated root look like? Well, it looks like it just touches the graph. So what we're going to do is we're now going to start to plot on our points. Let's say that's 1, 2, 3, negative 1, negative 2, negative 3. So what we're saying is we've got a root here at negative 3. So we just label that on as negative 3. And we've got another root at a half. Right, so I'll just label that on as well. So that's a half. Okay. Yep. And we're saying that this root at negative 3 just touches the graph. And we know that the graph has got this kind of shape. So we can immediately say that we're going to have something like that here, where it touches the curve. Now, This point also corresponds with what we learned in part A, because in part A, we learned that we had a stationary value at x is equal to -3. And that thing there is a stationary point, isn't it? It's what we call a minimum point. So actually things are nicely matching up. Okay, well, I think we've got probably two other things to include here. So the first thing we want to include is the y-intercept. Where do we get a y-intercept? We get a y-intercept when x is equal to 0. Okay, so if x is equal to 0, we've got 0 times 0 minus 1, which is -1. And we've got 0 plus 3, which is 3, all squared, which is 9. So we've got -1 times by +9, which is -9. We've got -9 times by -1/3, which is +3. So we also want to write something like that. So y-intercept when x is equal to 0, and that's going to give us y is equal to +3, right? But of course, you should probably do your working a bit more. So we've got y-intercept at +3. What's the other thing we want? We want the position of the other stationary point. And we learned in the previous question that the other stationary point had an x-coordinate of, what was it? -2/3. Okay, -2/3. So we want to find out where that y-coordinate is going to be. So that's where the x-coordinate is going to be. So let's just substitute in when x is equal to -2/3. By the way, I'm doing it up here so that I can actually see the polynomial, but your working really you try to make it neat on the page, because it just, I think, looks more convincing to an examiner. So we got 2 times by -2/3, which is -4/3 minus 1. And then we've got -2/3 plus 3 all squared. So let's try to simplify that. -1/3. -4/3 minus 3, well, minus 1. Well, that's -3/3. So that would be -7/3. And we've got -2/3 plus 3. So plus 3 is +9/3. So that there would be 7/3 all squared. So we are going to end up with 7/3 cubed and then divided through by 3. So let me get my calculator out. All right, so, oh dear, we have got 7 divided by 3, so 7/3. I'm going to cube that. Yeah. Cube that. Okay. And then the negatives cancel out, and I've got to divide through by 3. So I get that is 343 upon 81. So 343 over 81. And I want to see what that looks like roughly as a decimal. That is equal to 4.23. Okay, so if we were to indicate that on a graph, let's say this is 2, 4. So our so I'll label that like 2, 4. This guy's going to be 3, right? 1. Then we know that our y-intercept is here. The graph goes through there. And our stationary point is going to be like somewhere there, I guess. And that's going to be a maximum point, isn't it? So now we can just join up the graph. Let's try to get this looking nice if I can. Like that, like that. So that's the stationary point. It's going to come down. It's going to go through the y-intercept. And it's going to go through the x-intercept there. So just try to make that look a bit nicer. And so that should be my graph. Okay. Sorry about that. Bit weird looking at the end. Okay, now I'm just going to go through the mark scheme. I just want to highlight to you what we're asked to do. So we get 1 mark for the correct cubic shape and the maximum point in the correct quadrant, right? So that maximum point's got to be in the left-hand side top. Another mark for correct cubic shape touching at -3, so you've got the repeated root gets you a mark, and passing through a half, x is a half, so the other x-intercept, and the intercepts must be marked, right? So actually you've got to do quite a lot there. Your shape needs to be correct to get that mark. You need to have the 2 x-intercepts to get the mark. The 2 x-intercepts must be labeled, by the way. It really, sorry, I'm going to complain. It really frustrates me when students don't label it, because you're throwing your mark away. and you have to have the repeated root kind of correctly drawn. Okay, third mark, for correct cubic shape passing through 0, 3, the y-intercept, and the intercept must be marked. Okay, all right. Okay, so that is that. I hope that was helpful. Okay, then last part of this question, part C. Find the values of k such that q of x equals k has exactly one solution. Well, what does this thing here mean? This thing is like saying it is the intersection of the two curves, which is y equals q of x. And it's not a curve really. The line y is equal to k, where k is a constant. Well, what does y equal k look like? If I was to go back up to my graph, y equals k is just going to be a horizontal line like that. So, for example, this would be y is equal to 2, like that. Now, how many intersections does that have? That would have 1, 2, 3 intersections. Now, we don't want 3 intersections. What we want is we want 1 intersection. So where are we going to get that? Well, if I am here, if I am below the x-axis, then what I'm going to have is I'm just going to have 1 intersection, right? So if my k is less than 0, so my y value is less than 0, I'm going to have 1 point of intersection. But if I'm actually on the x-axis, right, like that, then I'm going to have 2 points of intersection, because remember the graph touches there. Okay, so I can't have that. So firstly, k needs to be less than 0. It can't be less than or equal to, it has to be less than. And I just need to extend my graph a little bit. Sorry about that. And we could also have 1 point of intersection here, if we are like that, because there'd be 1 point there. Now, what's the kind of the lowest we can go with that graph? The lowest we could go would be here, where the line would just touch the curve again at the maximum point, right? There would be 2 points of intersection, there and there. So we need to be higher than that point. Now, what's that point? We already calculated it. It was the maximum value, which was 343 upon 81. So we also need to state that k must be less than 0 and k must be greater than 243 upon 81. Okay, I'll just check the mark scheme again, make sure that I've got that right. Yep, so k must be less than 0, that gets you 1 mark, and k must be greater than 343 upon 81, that gets you 2 marks. Why? Because you get a method mark for finding that value, but actually, to be honest, you should have done that already when you sketched your graph. Okay, all right. Okay, question 7, we want to solve this equation here, giving our answers in exact form. Well, this kind of question is one in which we need to use a substitution, basically. So I'm going to say let u equal x to the power of a third. Sorry, I just wanted to double check that I got that right. That means I can rewrite this equation as 6u minus 2u to the power of negative 1 minus 1 is equal to 0. And you can rewrite that if you prefer as 6 minus 2 upon u minus 1 is equal to 0, because u to the power of negative 1 is the same as 1 divided by u. That's the indices rule. And then what we want to do is we want to multiply everything through by u. So we get 6u squared minus 2 minus u is equal to 0. And hopefully you will notice that this is a quadratic. So 6u squared minus u minus 2 is equal to 0. And it's probably a good idea to see if we can factorize this. Well, we're looking for two numbers that are going to multiply together to give negative 2. So it's either going to be negative 2 and positive 1, or positive 1 and negative 2. Let me see. I think I will make that into 2u and 3u there. So I'm going to get 2u times by negative 2 will give me negative 4u, and then 3u times by positive 1 will give you positive 3. So negative 4u plus 3u is negative u, right? So that's all right. And then 3u times by 2u is 6u squared. You can use a calculator to factorize or solve. Also, that's fine. Or you can use the quadratic formula. But I think it's a good idea to practice factorizing as well. Now, this means that we've got two options, right? 3u minus 2 is equal to 0, which means that u is equal to 2/3. Or 2u plus 1 is equal to 0, which means that u is equal to minus a half. Now we need to remember that we use the substitution x is equal to a third. So x is equal to a third is equal to 2/3, and x is equal to a third is equal to negative a half. So the power of a third is the same thing as the cube root. So if we want to get x, we just need to cube both sides, right? So we're going to cube 2/3, right? Or cube, beg your pardon. And we are going to cube negative a half. And if we cube 2/3, then what we're going to get is we're going to get 2 cubed, which is 8, over 3 cubed, which is 27. So that's one solution. And if we cube the negative a half, right? Well, negative times a negative times a negative is a negative. And then we're going to get 1 upon 2 cubed, which is negative 8. So we should get 8/27 and negative an eighth. I'm just going to check that that is right. Yeah, 8/27 and negative an eighth. Okay, so we're in question 8, which is a binomial expansion style of question. The first 3 terms in descending powers of x. That's a little bit unusual. Very often you're asked in ascending powers. In this expansion can be rewritten in this form here, where n, a, b, and c are integers. Find the values of n, a, b, and c. Now, I must say, I think this question is hard, but in a way, it kind of looks a lot harder than it is. Once you start it and you get past a certain point, the rest of it is actually quite straightforward. So let's try to figure this one out. So the first thing I think is we just want to expand the expression. So we've got 2x squared minus 1 upon 4x. So I'm going to write that as plus negative 1 upon 4x. I always think that's a helpful thing to do. All to the power of n. Let me just clarify that is negative there, so it doesn't look like that. Now, if we expand this, what we're going to get is we will get nc0 2x squared to the power of n, and then negative 1 upon 4x to the power of 0. Now, we just want to check that we are actually going to get descending powers of x. That means we're going to start with bigger powers and get smaller powers. If we want descending powers of x, then we want that guy, the 2x squared, to be raised to the power of n first, right? If we did it the other way around, if we had negative 1 upon 4x to the power of n, then we'd have a smaller power of x that would then increase. Okay, so you just want to be a little bit wary of that. There's a potential trap there. Okay, well, let's just keep expanding. This will be nc1, 2x squared to the power of n minus 1, times by negative 1 upon 4x to the power of 1. And then the next term, nc2, 2x squared to the power of n minus 2, negative 1 upon 4x to the power of 2, plus ... Okay? All right, then. Now, we know that this expansion can be compared with this guy here. So I think, firstly, what we can do is we can start our comparison by looking at the first term. So we know that this guy should be comparable with 256x to the power of 6. So let's try to sort that out. Okay, so we're going to say 256 x to the power of 16, sorry, x to the power of 16 is equal to nc0. Now, nc0 is 1 because anything c0 is 1, right? 5c0, 6c0, 7c0 is 1. That's a useful thing for you to know. You can verify it now by looking at the calculator. So I suggest you try to memorize that. Now, this guy here, 2x squared to the power n, there's a massive trap here. This is 2 to the power of n times by x squared to the power of n, which is x to the power of 2n. A lot of people are going to ignore the n here as a power of 2. Okay, they're going to write 2x to the power of 2n. Remember, if I've got a times b to the power of n, then I have a to the power of n times by b to the power of n. In other words, both elements in the inside the bracket get raised to the power of n. Okay, let's get rid of that. And then multiply by negative 1 upon 4x to the power of 0. Well, anything to the power of 0 is 1, right? So that guy is 1. So therefore, what we've actually got here is 256 x to the power of 16 is equal to 2 to the power of n times by x to the power of 2n. Well, if that's the case, we can just compare, can't we? We can compare the 16 with the 2n. So we can write, therefore, 16 is equal to 2n, and that means that n must be equal to 8. And we can check it by doing 2 to the power of n. So we've got 2 to the power of n. Sorry, 2 to the power 8, beg your pardon. And that gives us 256, right, which is what we should expect. So we now know n. And once we know n, actually the rest of this question, it basically unlocks. Okay, so I can take this. I'll just rewrite out the expansion, actually. I think it's probably just easier. So we've got 2x squared plus minus 1 upon 4x, I think, was it? 1 upon 4x, now raised to the power of 8. And I think it's just easiest just to expand it. So 8c0, 2x squared to the power of 8, and then negative 1 upon 4x to the power of 0, plus 8c1, 2x squared to the power of 7, negative 1 upon 4x to the power of 1, plus 8c2, 2x squared to the power of 6, negative 1 upon 4x to the power of 2, plus ... Okay. All right. Now then, we just simplify all this. Well, we already know the first term is 256 x to the power of 16, so there's no need to work through that again. 8c1 is 8. We need to do 2 to the power of 7. So 2 to the power of 7 is 128. So 128 x to the power of 14, right? Because x squared to the power of 7, we multiply the powers, times by negative 1 upon 4x, like that. We're going to do the next term now. So plus 8c2. So 8c2 is 28. And then we're going to get 2x squared to the power of 6. We want 2 to the power of 6, which is 64, times by x to the power of 12, because x to the power of 2 to the power of 6, again, we multiply the powers. And then this guy here, if we square it, well, negative times negative is a positive, right? And then we're going to get 1 upon 4x all squared. And so we're going to get 4 squared, which is 16, and x squared there, which is x squared. So now we just go through the last stage of simplifying this. So we get 256x to the power of 16 plus, not plus, sorry, minus, right? Because we've got the negative there. 8 times by 128 divided through by 4, which is 256. And we've got x to the power of 14 divided by x to the power of 1. So we subtract the powers, we get x to the power of 13. And then for the last term, we have got 28 times by 64, and then divided by 16, which is 112. And we've got x to the power of 12 divided by x to the power of 2. So we subtract the powers, we get x to the power of 10 there, plus ... So now we can just do a straightforward comparison, isn't it, right? So our coefficient of x to the 13 is a, according to the question. So a is going to be negative 256, right? So let's write this down. So firstly, n is equal to 8. A is equal to negative 256, right? Let's go back up to the question. This term here, the b is the coefficient and the c is the power. So let's go down. So what's our coefficient here? 112. So b is equal to 112. And what's our power? It's 10. So c is equal to 10. So I get that we get those 4 values. Now I'm just going to double check that against the mark scheme just to make sure that, that I haven't made a mistake somewhere. So n is 8, a is negative 256, b is 112, and c is 10. Yep, those are all the right answers. All right, so here we are in question 9. We're given this function here, y is equal to this. We want to differentiate it to show that we can get this where a and b are integers. Now, in this question, we've got one function divided by another function. And if we've got one function divided by another function, then we need to use the quotient rule, right? So we're going to label the function on the top u and the function on the bottom v. Now, let me just check the power for u. that's a third, right? Sorry, I had to look very carefully. You want to be super careful with that, by the way. So it's very easy to misread it as a half. And then v is x minus 1 to the power of 2. Now, we're going to have to differentiate both of these. So if I differentiate this thing, I've got a chain rule. So the way I do that is I differentiate the big bracket by bringing the third down to the front and reducing that power by 1. So if I do that, I'm going to get a third, big bracket, 5x plus 2 to the power of negative 2/3. Okay, then I'm going to differentiate the inside the bracket, and I get 5. I multiply through by 5. Next, if I do the same thing with v, I differentiate the big bracket, so I get 2 bracket x minus 1 to the power of 1. And then I differentiate on the inside. So if I differentiate x minus 1, I get 1. I multiply through by 1. By the way, even though that thing seems totally redundant and unnecessary, I strongly recommend you do it just so that you keep building the muscle memory of having to do the chain rule properly. Okay? All right, now then, what is the quotient rule? The quotient rule is v du minus u dv all over v squared. So now what we've got to do is we've got to substitute everything in, and hopefully it should all cancel out properly. So v is x minus 1 all squared. That's going to be times by 5/3, 5x plus 2 to the power of negative 2/3, minus u, which is 5x plus 2 to the power of a third, times by dv, which is 2 bracket x minus 1. And all of this is over v squared, which is x minus 1 squared squared, which is x minus 1 to the power of 4. Now, this looks very nasty, but when you're dealing with a question like this, can I suggest that what you do is you focus on the power on the numerator, which here happens to be negative. So in other words, that guy, that is the guy we do not like. That is the guy we want to get rid of. How are we going to get rid of that guy? Well, we multiply the entire numerator by effectively the equivalent expression, but with a positive power. So we are going to multiply by 5x plus 2 to the power of positive 2/3. Why is that going to work? Well, because if you imagine, if I multiply that by this, then what's going to happen is I'm going to add the powers. I'm going to get negative 2/3 plus 2/3, which is 0, and anything to the power of 0 is 1. So in other words, what I've done is I've cancelled out these guys. Another way of looking at it is this thing, because it's negative, is the equivalent of 1 divided by 5x plus 2 to the power of 2/3. If I do 1 divided by 5x plus 2 to the power of 2/3 times by 5x plus 2 to the power of 2/3, I get 1. All cancels out. So let's multiply through. Here what we are going to get is x minus 1 squared times by 5/3 times by 1, because it cancels off. Then I'm going to get 5x plus 2 to the power of a third times by 5x plus 2 to the power of 2/3. So what am I going to do? I'm going to add up these powers. And a third plus 2/3 is 1. So that guy is 5x plus 2 to the power of 1 times by 2 bracket x minus 1. Now, we need to remember, right, if we multiply the entire top by 5x plus 2 to the power of 2/3, we've also got to multiply the bottom. Why is that? Because we've got equivalent fractions, right? So whatever I multiply on the top, I've also got to multiply on the bottom. So here we're going to get, on the bottom, x minus 1 to the power of 4, x minus 1 to the power of 4, times by 5x plus 2 to the power of 2/3. And now what I'm going to do is I'm going to try to simplify a little bit. Now, the first thing I'm going to do is I'm going to factorize out this x minus 1. And I think probably the easiest way to do that is actually just to straight cancel. So I'm going to divide through by x minus 1 on the top. So that disappears, and that becomes a 3. Now, just a note on that. A lot of students who are a little bit weak in their algebra think that when you're factorizing, it's like if you see something on the top and if you see something on the bottom, then you can like cancel it off. So like, you know, I see a 5 on the top and I see a 5 on the bottom, therefore I can just chop, chop. It's not like that. What's happening when you are canceling is you are actually dividing top and bottom by the same thing. So I've got to divide the entire top by x minus 1, which means I've also got to divide the entire bottom by x minus 1, right? So if I get this guy divided by x minus 1, x minus 1 squared just becomes x minus 1. This guy, if I divide it by x minus 1, I get 1 because it fully disappears. And x minus 1 to the power of 4, if I divide it by x minus 1, I get x minus 1 to the power of 3. Okay, so that's what's happening there. Okay, so then let's go forward and simplify this. I'm going to get 5/3 x minus 1 minus 2 lots of 5x plus 2 all over x minus 1 to the power of 3 times by 5x plus 2 to the power of 2/3. Now, we've got another fraction within a fraction. We've got this 5/3 here. That's not very nice to have. So I think the best way to get rid of that is we're going to multiply top and bottom by 3. Multiply top by 3, multiply bottom by 3. And if we do this, then 5/3 is just going to become 5. Sorry, I'm not going to write out the whole thing again because it's just a bit tedious. And then the negative 2 times by 3 becomes negative 6. So that guy there is negative 6. And of course, we've got to do the same thing on the bottom. So I'm going to get 3 on the bottom because of the equivalent fraction idea, right? So the whole point is, in each of these steps, we're multiplying the top and bottom by the same thing. We've got to multiply the whole top. We've got to multiply the whole bottom. All right, then. We're getting close. On the top, we can now simplify our terms. We've got 5x minus 30x, right? So 5x minus 30x is minus 25x. And we have got, as well, 5 times by negative 1. So minus 5 minus 12, it looks like. Minus 5 minus 12, which is minus 17. So we've got minus 25x minus 17, all divided through by 3 bracket x minus 1 cubed bracket 5x plus 2 to the power of 2/3. Now that looks like we're close to the answer. What was the form we needed to have? We needed to factorize it on the numerator. Well, we factorize out negative 1, then that would become like that with a positive there. So I think my value of A is 25 and my value of B is 17. I'm just going to check that against the mark scheme. Just always check. Where are we? Yeah, 25 and 17 is the right answer. All right, so this is question 10, which is a circular measure style of question, a radians question. Now, just on a practical note, right, if you're doing this question in exam, before you do anything, please set your calculator to radians mode. Because once you're halfway through the question and then you begin to use your calculator, it's so easy to forget that your calculator is in degrees. Okay, so please, please, please do that. I strongly recommend you do it as the first thing. Okay, now let's try to get a handle on this question. The diagram shows the sector OAB with center O with radius 20. Okay, so that means that also this length here is also going to be 20, isn't it? So we label that on. The perimeter of this sector is 65. So that perimeter there is going to be 65. Okay. The lines CA and CB are both tangents to the circle at the points A and B. So that line and that line. And if it's tangents to the circle, it means that it's going to make an angle of 90 degrees with the radius, which is also indicated on the diagram. I'll just highlight it there. Right. So if you're not sure, when it says tangent to the circle, it always means it's a right angle with the radial line. Okay. So that the triangle ABC, so ABC is isosceles. If it's isosceles, it means that these two lines are identical in length, okay? Same length there. The angle AOB is equal to theta. That's that angle there. Want to find the area of the shaded region. Okay, now, one of the biggest problems here is you are going to make assumptions and you're going to make lazy assumptions. And I think a massive trap here is you're going to look at the shape and go, whoo, that looks like a square and it's got right angles in it. So it must be a square. Never, ever, ever assume something that you do not know 100% to be true. Okay, that's going to be really dangerous in these questions. So you want to be extra, extra careful. Okay. Now, how can we proceed? Well, the first thing we want to do is we want to find that angle there. How are we going to find that angle? Well, we've got one bit of information. We know that the perimeter of the sector is 65. Okay. Now, the perimeter is going to be this length 20 plus this length 20 plus this length here, which is the arc length. Now, the arc length of a sector is given by the radius times by the angle r theta, so long as theta is in radians. Okay. So what we can say is that the perimeter here, P, is going to be equal to 20 plus 20 plus r times by theta. So r is 20 and theta is the unknown angle. Now we know that that perimeter is equal to 65. So we can say, all right, 65 is equal to 20 plus 20 plus 20 theta. Well, if we subtract 40, we're going to get 25 is equal to 20 theta. And if that's the case, then theta is equal to 25 upon 20. We can divide that by 5, we get 5 upon 4. So this is 5 upon 4 radians. That's the first thing. Now, by the way, 5 upon 4 radians is not the same thing as pi by 2, which means that that angle there is not 90 degrees, right? It's not a right angle. And if it's not a right angle, then this shape here is not a square. Okay, so that should also tip you off. All right then. What's the main objective? The main objective is find the area of this region here. How can we do that? Well, we need to find the area of this big object, the kite, to give it its proper name. And we need to find the area of the sector. Well, let's do the area of the sector first, because that should be quite easy to do. The formula for the area of a sector is a half r squared theta, again, where theta is in radians. So I'm going to write this down. The area of the sector, by the way, you should always write in words what you're finding, just to make it nice and clear to the examiner, is equal to a half times by 20 squared times by theta, which is 5 upon 4. Okay, now I'm going to key all this into a calculator because I don't want to make a slip with my arithmetic. Okay, so 20 squared times by 5, divide by 4, and then divide by 2. I get that as 250. Okay, so 250 centimeters squared, I guess. Okay, then what we need to do is we need to figure out how we can find the area of this object here. Now, this guy's a right angle. We can use the fact that it is a right angle, and the way we're going to do it is we are going to split up our shape. I'm going to draw a line straight down here, like that. And the reason I'm going to do that is because I'm going to make it clear that what we've got is we've got a triangle, and we've got a right angle triangle. And when we've got a right angle triangle, the area of a right angle triangle is just going to be a half the base times by the height. Well, we know the base is 20. The thing we need to find is we need to find that there, the height. So let me give that a letter. Let's call that H. And it means we also need to know that angle. Well, that angle is going to be a half of the angle theta. So if that's 5 upon 4 radians, a half of that is going to be 5 upon 8. Now, that means that we can use a tangent, doesn't it? Because tan of that angle is equal to the opposite h over the adjacent, which is 20. So I can write down, if I go down, so I try to do it maybe on the right, that tan 5 upon 8 is equal to opposite h over 20, and therefore h is equal to 20 times by tan 5 upon 8. Now then, now that we've got that, everything else should hopefully be relatively straightforward, because we want to find the area of the triangle, of our little green triangle. I'm going to write that down. The area of a triangle is equal to a half the base times by the height. The base is 20. The height is that h. So we've got a half times by 20 times by 20 tan 5 upon 8. So that's going to be 10 times by 20, isn't it? Which is 200 tan 5 upon 8. And so then the area of the shaded region. Well, what's the area shaded going to be? That's going to be equal to 2 of those triangles. So we've got 2 lots of triangles. So we've got 2 times by 200 tan 5 upon 8 minus that area of the sector, which is 250. Now notice that so far I haven't yet keyed anything into my calculator, and I strongly recommend that you do the same, right? So always never have things as decimals, always have everything as exact values until the very final step, and then you key it in. Okay, so now I'm going to look at my calculator. I'm going to again check that it's in radians. I'm going to find the tan of 5 upon 8. I'm going to times that by 200 times by 2, so times by 400. which gives me 288.6. And I'm going to subtract off 250, and that gives me 38.59, or 38.6 centimeters squared. Now, what I'm going to do is I'm just going to check that against the mark scheme, make sure that that is right. That's question 10. So let's go down. Question 10. Answer is 38.6. Yeah, so that's correct. Okay, now let me just talk about that question very briefly. Firstly, this whole thing with the right angle triangle has come up quite a few times, I think, in the last few years. And it's been very useful to be able to spot that you can find the area of it by doing half base times height, and that this side length here can be found out using the tangent, right? Using a tan is equal to opposite over adjacent. That's happened a couple of times. Okay, so I think you want to try to just be aware of that, that's a way of doing it. The other thing I would say is again what I said at the beginning, which is you just want to be really careful with these questions that you are not making assumptions, okay? Build on what you know, not what you guess. And sometimes the images you are given can be sort of, I suspect, deliberately misleading, right? They can trick you. So just be super, super careful. Just because something looks like a square or a rectangle or whatever, do not assume that it is, okay? Unless you know, do not assume. Okay, I hope that was helpful. All right, so here we are in a vectors question in the triangle OAB. OA is the vector A, OB is the vector B, and the straight line XYZ is such that O to X is 4/5 of B, A to Y is 1/3 of AB, A to Z, so A to Z, where is that? That guy there, is equal to mu A, and Y to Z, which is that guy there, is equal to lambda of XY, which is that. We want to show that X to Y is equal to 2/3 of A minus 7/15 of B. Well, we want to ask really the question, how can I go from X to Y, right? How can I travel from here to here? And what I would suggest is you just think about walking along this diagram, right? I can go from X to O, then I can go from O to A, and then I can go from A to Y, right? So I can write this out as X to O plus O to A plus A to Y. Okay? And that should all make sense, right? I start at X, I go to O, then from O, I go to A, then from A, I go to Y. So that should be a valid vector equation. Well, then we just got to fill in what this guy is. Well, the vector X to O is the opposite of going O to X, right? So I can actually replace XO with minus OX, like that. OA, well, that's just the vector A, isn't it? And AY, well, AY in the question we're told is 1/3 of AB. So I'm going to replace AY with 1/3 of AB. Okay, well, now then, OX, we're told in the question. Beg your pardon. OX is 4/5 of B. So I'm going to replace that there with minus 4/5 of B plus the vector A plus 1/3 of AB. Now, what's AB? AB, many of you hopefully will know, is OB minus OA, but I'm just going to try to show why that's the case, right? A to B is the same thing as going A to O plus O to B. Right, so A to O plus O to B. But what is that vector A to O? Well, it's the opposite of going O to A, right? So this guy here, AO, is the same thing as minus OA. So I can replace that there. Say that guy is minus OA. And that's why the vector AB is the same as OB minus OA. So now it's just a case of simplifying, really. We've got this thing here. We've got minus 4/5 B plus A minus 1/3 of OA. Well, OA is just the vector A, and plus 1/3 of OB. So it's plus 1/3 of B. So let's collect together the A terms. We've got A minus 1/3 of A, which is 2/3 of A. And we've got minus 4/5 of B plus 1/3 of B. Well, and let's just go to the to the right-hand side, and we calculate minus 4/5 plus a third, which means we've got to give everything the same denominator. So I'm going to turn the fifth into 15ths. So it's minus 12 upon 15 plus 5 upon 15, and that's negative 7 upon 15. So that's minus 7 upon 15b. Okay, now is that what we were asked to show? Yeah, 2/3 a minus 7/15 b. That is our answer. Okay, we're continuing on our vectors question. So part B, we want to find y, z in terms of lambda, a, and b. Well, if we're finding it in terms of lambda, we need to go back up to our question here and see where lambda appeared. Lambda appeared in this bit of information that yz, that thing there, is equal to lambda xy. So I'm going to write that down. Yz is equal to lambda xy. Ooh. Yz is equal to lambda xy. And we've already calculated xy, right? Because that's what we did in part A. So we can write this as equal to 2/3 lambda a minus 7/15 lambda b, right? So in other words, I just take this guy here, our xy, and multiply it through by lambda. All right, now we want to find yz in terms of mu a and b. Well, where's our mu? Our mu was here, wasn't it? Az is equal to mu ay. So a to z is equal to mu of, where is that? Sorry, az is equal to mu a, beg your pardon. So let's write that down. Az is equal to mu a. Well, hang on, we're not asked to find az, we're asked to find yz. So how can I get yz? Well, I can say that y to z must be equal to y to a plus a to z, right? That makes sense. I start at y, I go to a, then I go from a to z. Now, do I have an expression for ya? Well, I have an expression for ay, don't I? Right? So ya is the same thing as minus ay. And so we know that that's got to be equal to minus 1/3 AB. So I'm going to go down here. This guy is equal to minus 1/3 AB. Sorry about there's not enough space, is there, to do this question. So I'm going to have to skip a bit of steps. Okay, so minus 1/3 AB. Well, we already figured out that AB is B minus A. We did that in the previous part of the question. And a to z, if we just go up, is mu a, right? That's the thing there. So az is mu a. All right. So I've got plus 1/3 a plus mu a. So I can write that as 1/3 plus mu a. And now I've got minus 1/3 b. Okay, so that's what I've got. Now, part D, sorry that I've run over, is hence we want to find the values of lambda and mu. Well, the key thing to notice is we've got two vectors that are yz, that's here and here. So these are equivalent vectors, which means that the bits of A are the same and the bits of B are the same. So we can compare. So I'm going to write here comparing. Let's compare the A's. Okay, so if I compare the A's, from the first vector, I've got 2/3 lambda, and the second vector, I've got 1/3 plus mu. So I can write 2/3 lambda is equal to 1/3 plus mu. Well, I think it's probably just easier if I multiply everything through by 3. So I'm going to get 2 lambda is equal to 1 plus 3 mu, right? So that's the first thing. Second thing, B, if we compare those, then for the first vector, we've got negative 7/15 lambda. So negative 7/15. Negative 7/15 lambda is equal to, well, what have we got for the second vector? We got negative 1/3. Right, so I can write that out as negative 1/3. Well, I think I can just straight away multiply, can't I? So lambda is going to equal to 1/3 times by 15 upon 7, because the negatives cancel out. 15 divided by 3 is 5. So we're going to end up there with 5/7 is lambda. And if that's the case, I can substitute into my top equation. So I got 2 times by 5/7. So 2 times by 5/7 is equal to, so I'm just substituting into here, just so you can see, is equal to 1 plus 3 mu. 1 plus 3 mu. So that's 10/7. 10/7 is equal to 1 plus 3 mu. Why don't we multiply everything through by 7, I think. So 10 is equal to 7 plus 21 mu. So 3 is equal to 21 mu. So mu is equal to 3 upon 21. And 3 upon 21 should cancel, I think, to give 1 upon 7. So let me just check that. I get lambda is 5/7 and mu is 1/7. Let's just see if that's right. Where I'm looking. Yeah, lambda is 5/7 and mu is 1/7. That is the answer. Okay, and always a good idea, by the way, I think with these questions, just check if it makes sense. Just look at the diagram, right? If lambda is 5/7, then we expect that y to z is 5/7 of x to y. Where is that? YZ is 5/7 of x to y. Yeah, okay. Yeah, could be. And a to z is equal to 1/7 of a. So that there is 1/7 of that. Yeah, I think that makes sense. Okay. All right. Next question. All right, so here we are in question 12, which is a trigonometric equation style question. Now, it's only worth 5 marks, and I know that some of you are going to be able to do this quite quickly, and the method I'm about to employ may seem long and cumbersome and unnecessary. But one of the things I notice with these kind of questions is that students are, to some extent, guessing the answers, and that can often be seen because they're a bit uncertain about the number of solutions they have or how to get the other solutions. So what I'm going to do here is I'm going to take you through a slightly longer method, but the advantage of it is that it is thorough. So I'm hoping that if you're able to follow through my steps, at least you can understand what I'm doing, and hopefully then you can replicate it for yourself on another question. So I just encourage you to be patient for this, because I hope that what I'm going to do is really going to help if you follow through. Now, the first part of this is if I've got a thing inside the bracket here, right, 2x upon 3 minus pi by 3, I'm going to replace that with a substitution. I'm going to call u 2x upon 3 minus pi by 3. And as I do that, I think it would also be helpful to rearrange this to get x in terms of u. So if I multiply both sides by 3, I get 3u is equal to 2x minus pi. And therefore, x will be equal to 3u plus pi, and then divided through by 2. Now, why have I done that? Well, because I want to change this slightly difficult problem in terms of x, with this domain of x, into a simpler problem involving u with a different domain for u. So I'm going to write 3 cosec squared u is equal to 4. And the domain, instead of x being between 0 and 3 pi, we're going to have 3u plus pi upon 2 between 0 and 3 pi, right? So in other words, I've replaced the x there with the expression in terms of u. Now, I'm going to try to simplify this. Now, first things first is that cosec squared will be equal to 4 upon 3. I divide both sides through by 3. And cosec is the same as 1 divided by sine, right? We always look at the third letter, 1, 2, 3. The third letter is s, so this is 1 divided by sine. So I write that out in full as well. So 1 upon sine squared u is equal to 4 over 3. And of course, if I flip those fractions, then what I'm going to get is sine squared u is equal to 3 over 4. And I can square root both sides to get sine u is equal to the square root of 3 upon 2. But remember, I need to have plus or minus here, because when I square root, I get 2 alternative solutions. So that thing there is very often missed out. And if you miss that out, you're going to miss out 2 or maybe even 3 solutions. Okay, so we've got a simpler problem now. Sine u is equal to plus or minus root 3 upon 2, but we need to get the right domain. So we need to rearrange this so we know what values of u that we want. So the way I'm going to do that is I'm going to take this inequality and I'm going to multiply all through by 2. So 0 times by 2 is 0. And then this will be 3u plus pi. And then 3 pi times by 2 is 6 pi. Now, beg your pardon. That thing there should not be less than or equal to or greater than or equal to. Let's get rid of that. That should just be that symbol. Now what I'm going to do is I'm going to subtract pi from every part of the inequality. So that will become minus pi. The thing in the middle will become 3u. And 6 pi becomes 5 pi. And then I'm going to divide everything through by 3. So I'm going to get minus pi by 3 u and 5 pi upon 3. So just to clarify, what have I done? I've taken this harder problem involving x with a domain for x, and I've made it into a slightly simpler problem, which is just in terms of u and has a domain for u. Right, so now what I want to do is I want to solve this guy. Now, there are a couple of different ways I could do this. I could use the graph, or I could use the unit circle. Now, for those of you who are using something called the quadrant method, basically what you're doing is you are using the unit circle. You're just not aware of it. So let me draw out the unit circle. The unit circle is the circle with radius 1. Okay, so I'm going to try to draw. Oh dear, it's not very good. Try that again. Okay, so this is the circle of radius 1. I'll try to make it look as nice as I can. Okay, now let me just try to explain why this is helpful. Basically, sine and cosine, they come from this circle of radius 1. Let me try to explain how that is. Imagine that I've got a point here. The point here is the point P, and that point has got an x-coordinate and a y-coordinate. Okay, and that point P makes an angle of theta with the positive x-axis, right? So that there makes an angle of theta. Well, this x-coordinate, its value is given by the cosine of that theta, and this y-coordinate there is given by the sine of that angle theta. So in other words, what I want you to see is when we talk about cosine theta, what we're really talking about is the x-coordinate on this circle. And when we talk about sine theta, what we're really talking about is the y-coordinate on this circle. So if I want to kind of clarify that idea, here the angle is 0. Let's see on there the angle is 0. Okay, so what's the x-coordinate? The x-coordinate is 1. Well, cosine of 0 is 1. Okay, well, let's go here again. The angle is 0, and the y-coordinate is also 0. Well, yeah, the sine is also 0, right? Sine 0 is also 0 because sine tells you the y-coordinate. Let's go up to here. This angle is going to be pi by 2 radians or 90 degrees. Well, what's cosine 90? Cosine 90 is 0. Well, yeah, if I'm here, the x-coordinate is 0, right? The x-coordinate there is 0. What's sine 90 degrees? Sine 90 degrees is 1. And that makes sense as well because the y-coordinate is 1. So this is a really big idea. It's really useful, I think, for you to understand that when we talk about cosine and sine, what we're really talking about is we're talking about the x and y coordinates on this circle. Now, how can we use this information? Well, what we're going to do, get rid of all of that there, is we want to find where sine u is equal to root 3 upon 2. Right? Well, that means what we're really asking is where is the y-coordinate equal to root 3 upon 2, right? Because sine is the same as the y-coordinate. So what I'm going to do is I'm going to draw a nice straight line there, and that line is y is equal to root 3 upon 2. Okay? And so our solutions are going to be the intersection points of our circle and that line. And so what we're asked to do really is to find this angle here, and also then this angle here, which I'll draw in blue, right? That angle there. Okay. Now the angle in red we can get from our calculator, and that angle is going to be pi by 3. And by symmetry, hopefully you can see that this angle here on the other side will also be pi by 3. Right. So this point, that point there, is symmetrical with that point there, which means that this angle here is going to be symmetrical with that angle there. So how can we find this blue angle, right, that angle there? Well, it's got to be pi radians minus pi by 3. Why is that? Well, because the angle that takes us from here is pi, and then if we go back pi by 3, we're subtracting pi by 3. So we have got solutions for u, which are pi by 3 and pi minus pi by 3, which is 2 pi upon 3. Okay? All right then, well, we also want to find out where sine u is equal to negative root 3 upon 2. Well, that's going to be the same as asking where the y-coordinate is negative root 3 upon 2, so that's going to be there. So that's the line y is equal to negative root 3 upon 2. And so what we're being asked to find is we're asked to find that point and also that point. So we want to find this angle here. Let's put that on. This angle. Sorry about that. That angle. And also we want to find this angle here in green. So I will draw like that. That angle there. Okay. Now, this angle is the reflection of that angle, isn't it? Right? Those are going to be the same. So this angle here is pi by 3. So the way we can write that is to say that's negative pi by 3 because we're kind of going in the opposite direction. We're going in the clockwise direction. So that's minus pi by 3. Or alternatively, if you prefer, what we could say is we could find this angle here, right? And the way we would do that is we would do 2 pi radians, 1 full rotation, minus the pi by 3. So two ways you can think about it. It's either negative pi by 3, or you could say it's 5 pi by 3, up to you. Now, the angle in green, that guy, well, that's going to be pi radians plus another pi by 3. Why is that? Well, because that angle there, via symmetry, is also pi by 3. So what we've got here is we have got 4 pi by 3. Okay? Now, these represent our base solutions, right? We've got 4 solutions, but we need to be a little bit careful because we've got a domain from negative pi by 3 all the way up to 5 pi by 3. So we want to ask ourselves the question, are there any other solutions here? Now, the way you could get those other solutions is you can take any one of our solutions and go all the way around the circle one time, right? Because if I started here and I go all the way around the circle, in other words, if I rotate by 2 pi radians, then I'm going to get another identical solution. So therefore, what we're really saying is we can take any of these solutions, any of these guys, and we could add 2 pi or minus 2 pi from any of them and get another identical solution. Or another similar solution, beg your pardon. Now, if I add 2 pi, that's the same as adding 6 pi upon 3. So I'm just going to change that a little bit. Change that to 6 pi upon 3. And we're going to do that to each of these guys and see if they still fit within the domain. So pi by 3, if I subtract 6 pi upon 3, I get negative 5 pi upon 3, and that's out of the domain. If I add 6 pi upon 3, I get 7 pi upon 3, that's out of the domain. So u, pi by 3, that's the only solution for that. Now, if I get 2 pi by 3, if I subtract 6 pi by 3, I get minus 4 pi by 3. That's out of bounds. If I add 6 pi by 3, I get 7 pi by 3. That's also out of bounds. So 2 pi by 3 is the only one for that solution. Let's take negative pi by 3. Well, that guy isn't acceptable either because remember, this is a inequality here which isn't equal. So we can be greater than negative pi by 3, but we can't be equal to it. So that guy is not a solution. So let's add 6 pi by 3, see if we get another one. Well, if we add 6 pi by 3, we get 5 pi by 3. And 5 pi by 3 is a valid solution because we can be equal to that. So we're going to write that there. We've got 5 pi by 3. Okay. And then lastly, if I take 4 pi by 3, well, if I subtract 6 pi by 3, I get negative 2 pi by 3. That's out of bounds. If I add 6 pi by 3, I get 10 pi by 3. That's also out of bounds. So what I end up with here is I've got 4 pi by 3 is the only value there. Now, these are all the solutions we can have. I'm just going to change the order so they're nicely in order, if you don't mind. So 4 pi by 3 and 5 pi by 3. 4 pi by 3 and 5 pi by 3. And now what I'm really saying is we've got solutions for u. We want to convert these guys to solutions for x. Well, what's x equal to? X is equal to 3u plus pi upon 2. So x is equal to 3u plus pi upon 2. Well, I'm not going to be, I don't want to make a mistake here, so I'm going to do it step by step just to be sure. I'm going to multiply these all by 3, so that becomes pi, 2 pi, 4 pi, and 5 pi. Now I'm going to take each of those guys and I'm going to add pi to them. So I get 3u plus pi, so that's 2 pi, 3 pi, 5 pi, and 6 pi. And then what I'm going to do is I'm going to divide all these through by 2, so I get my x solution, and that becomes pi, 3 pi by 2, 5 pi by 2, and 3 pi. And those should be all of my answers. Now, I recognize that is a long way of working. I recognize that it may be more complicated than many of you are used to, but notice that I am getting the right answers, and more importantly, I can explain why. You want to aim for that as much as you can, guys. Try to explain why you're getting the right answers to yourself. Okay? All right. Now, I hope these videos have been helpful. If you are finding them useful and the explanations that go with them, please do like, please do subscribe, please do share with your friends. There'll be more content published shortly, and I wish you all the best with your upcoming exams. Bye-bye.